Okay, we established, first thing we established as far as magnetic fields, we took a compass and put it over the top of a wire and ran a current through the wire and the compass deflected. Okay, meaning that the wire created a magnetic field. That the current through the wire created a magnetic field. Well, what it is, it creates magnetic field as moving charges. First thing you need to understand to really understand magnetic field. Now, you say magnets create magnetic fields. Yeah. At the atomic level, you've got electrons that are, they're not really circling atoms, but they're acting in a way that's equivalent to circling atoms. And that's a loop of current. And that loop of current reinforces with other loops of current within the magnet and creates a magnetic field. Okay, so it's a combined magnetic field of all the little atomic loops of current. Now, it's a little more complicated, matter of fact, a lot more complicated than that. That's a good way to start understanding it. And that's true in pretty much the case of any permanent magnet. Okay. What responds to magnetic fields? Well, the answer I got was, well, magnets. Yeah. The magnet will respond to magnetic field. These wires will respond to magnetic field. Okay. Magnetizable materials respond to magnetic fields. And the reason is that the magnetic domains, which is, just think of clumps of atoms that are kind of oriented so that there's a net magnetic field in those little clumps. And those clumps are in random directions. You put a magnetic field through it in those little clumps, those magnetic domains, we call them, okay, line up a little bit. And now that piece of iron or whatever it is becomes temporarily a magnet. It acts just like a magnet and it responds to a magnetic field, both by aligning and becoming magnetic, so to speak. Okay. And well, that's kind of it. So the question is, what responds to magnetic fields if moving charges? Moving charges create magnetic fields. Moving charges respond to magnetic fields. Now, moving charge doesn't respond to its own magnetic field, but if you create a magnetic field in a loop of wire, as we've done, okay, by running a current through the wire, then you get a magnetic field inside that loop. And if you change the magnetic field inside that loop, you change the flux through the loop, right? So when you take the current off, the flux changes, which creates an EMF, a voltage, that opposes the change. It's something worth pondering. We'll work it out. It's not that complicated, but it's kind of neat. And one of the neatest things I think in physics called self-inductance. So, we're going to spend the latter half of the course assuming that everybody is well versed in all the transition problems. How many of them are there? Hundreds. Okay, maybe up hundreds, closer to 200. But each one of them is pretty straightforward, especially if you understand the ones that came before. Just kind of one-step problems, or 1.5 steps. Okay? So we want to understand all of that. And these are the two principles they're kind of behind most of the magnetism, whether you see it or not. Whether you see the connection or not. Okay, so here's the rule. A charge Q with velocity V. QV is a source of magnetic field. If you go to a point here, you got your R vector from position of the charge to the point. P. Cross product QV cross R. Got a proportionality constant. Okay. I just wrote a little word, a little abbreviation, CONST. Not written very well. Some constant times QV cross R. Okay. What are the units of QV? Kilometers per second, right? Now, previously in lab, I mentioned, I think I might have mentioned last, if you have a current, get a current I and a segment delta L, which we might regard as a vector. And we've got a point T. I delta L is a source of a magnetic field at P. Now, we're assuming delta L is a very short segment of current, and that the length of the segment is short compared to your R vector. It goes from some point within delta L to P. Same rule with magnetic constant. Okay. Same constant here is here. K prime's 10 to the negative seventh Tesla per amp meter. What's an amp meter? First of all, the units of QV are coulomb meters per second. Here, you have to find out L amp meter. Now let's put this together and let's talk a little bit first. Okay, so what's an amp? Well, I got a pretty quick answer. It should be right at the tip of your tongue at this point. That's a coulomb per second times a meter. Now, the units of QV are coulombs times meters per second. So QV has the same meaning, or the same units, at least, as an amp meter. These two formulas are saying the same thing, but in slightly different contexts. So, well, let me what was there? Does this unit make sense then? Tesla per amp meter? Well, what are the units of QV cross R? V has units coulomb meter per second, which is the same as amp meter, right? Be crossing with R, what would the units of R? I mean, it's units of length. So maybe you better have meter squared down. Okay. Well, look it up, ponder it, and think about it. Okay. Now I want to consider if you did have an electron moving around a proton, electrons in circular orbits about a nucleus. I should say, not really so, but it pretty much works most of the time. And by most of the time, I really should probably say in most situations. Most things you can measure. If you don't measure too precisely, this works out. Now, it didn't take them long to see that, oh, there's some anomalies here. Okay. You got angular momentum and you got fine splitting and you got all kinds of stuff. And that happens at the atomic level that isn't well explained by the boron. Still, it's a pretty successful model. It's a pretty good model. So we're going to use it just to understand magnetic moment in hydrogen. Okay, so electrons moving at about 10 × 6 meters per second, or if it's a proton, distance of 10 to the negative 10th, about meters. And those are just ballpark figures. We can easily figure out what these numbers ought to be. Actually, in the ground state, the electron has a mean distance from the nucleus of about 0.529 angstroms. 10 to the negative 10th meters is an angstrom. It's a tenth of a nanometer. Nanometer is a billion, 10 to the negative 9th. Okay, that's the numbers used in atomic molecular scale. And most atoms have a radius or diameter on the order of an angstrom. From an angstrom to maybe a few angstroms. Okay. Your most highly charged nuclei from the natural elements like uranium, okay, it's got nearly 100 protons in there and something like 150 neutrons. Okay, something like that. Actually, I should be able to figure that out. It's 238. So it'd be like 92 protons and 150, 646 neutrons. Anyhow, that attracts the electrons much more close, much more strongly than a single proton. Okay. So the electrons, they're like 92 of them, electrons are all pulled in pretty close so that the diameter of the uranium atom isn't a whole lot bigger than the diameter of a hydrogen. Okay. And there's subtleties in there that I don't even begin to understand about, I mean, at least not at the rigorous level. Related to the shape of the nucleus and the amount of shielding that the electrons inside the orbit of an atom, the amount to which the outer electrons are shielded by the inner electrons. If you're that last electron out here, you've got a whole lot of electrons in a cloud inside of your orbit. And by Gauss's law, you're basically only seeing a net charge of equal to one proton. Okay, if you got 91 electrons inside of you, that the outer shell doesn't do that actually. If you had 91 protons or electrons inside of you between you and the nucleus, you'd only be experiencing the electrostatic force equivalent to one proton. Okay, that's all there is to it. That's a direct result of Gauss. So you got that about atoms, but I'm digressing a little bit. Right now, we're just considering an electron orbiting a proton at approximate speed, and so forth. Now, you could figure out what the speed actually is. It's actually a fairly easy problem. You just set the centripetal force equal to the Coulomb attraction. Okay. And if I give you the distance, 0.529 angstroms, or 5.29 times 10 to the negative 11th meters, it's just like figuring the orbital speed of a satellite. Same principle completely. It's just that you've got Coulomb's law rather than universal gravitation exerting the force. Okay? So you can easily figure this out, but it's something on the order of 10 to the 6 meters per second, maybe a few times. I haven't worked on numbers. Okay? And I don't remember exactly what it is. So just ballpark. Okay, just giving you a little bit of idea of what kind of magnetic field you get from this thing. Okay? So my question now is, okay, this essentially gives you positive charge in the middle. And it's only a single electron, but it's moving around here at 10 to the 6 meters per second. And the total distance it moves is only on the order of 10 to the negative 10th meters. So it's moving around here like 10 to the 16th times every second. Well, 10 to the 16th is an unimaginably huge number. Okay. So it's just like you've got a continuous circuit running here. How many amps? Okay. So you can figure out then what the magnetic field of this loop is. Okay. You can do it by treating this loop as a current, or you could figure it out using the electron itself as a source. QV is a source. What's Q? 1.6 times 10 to the negative 19th coulombs multiplied by 10 to the 6 meters per second. What do you get? You get 1.6 times 10 to the negative 19th half meters. Negative 13, sorry. That right there's a source. You can use QV cross B, QV cross R. R is just a vector. If Q is here, I mean, if Q is here, here's your R vector. If you want the field at the center of this loop, you just multiply QV times R because the R vector is perpendicular to the velocity vector. And multiply that by your K prime. Oh, wait a minute. You know, I really messed up. And so hung up QV cross R. It's an inverse square. And so is this. And ours, this thing's a unit vector, so I just wrote them down. So these units, which I was intentionally ambiguous about, aren't what I said they are. If you multiply this by this, you don't get Tesla. And what I really wanted to leave for you is, how do you get to Tesla here? But B has to be in Tesla. QV over R now has units. Kilometers per second divided by meters. Okay, not meters squared. So what's that do to your units? I'm going to leave you to figure that out because I'm assigning the transition problems. They've already been assigned. By the end of this week, you're supposed to have them, but you'll probably spill that over into spring break. Okay. So I got up the wrong side of the bed. This was making too many mistakes. But it's an inverse square function. Realize that. Here. So QV over R squared is then going to be equal to 1.6 times 10 to the negative 13th meters divided by square of 10 to the negative 10th meters. And the instant when this thing's moving around here, this turns out to be magnetic field in the order 10 to the 7th Tesla. Somehow that doesn't seem right, so be sure you learn to think this through. Okay? Here's an inverse square. I mean, the only places you see magnetic fields like that are in the vicinity of neutron stars and things like that. Can't produce that magnetic field on Earth. I don't think we've even been able to produce 100 Teslas. A 1 Tesla field is extraordinarily strong. Nuclear magnetic resonance machine, a few Tesla, maybe up to 6 or 7. Okay, so take that for what it's worth, but there's the model of an electron orbiting a proton. The idea then is you've got this atom, it's actually a current loop with a strong magnetic field. QV cross R will be out of the plane of the loop. And you're familiar with that from things we've seen in lab. Okay. So you got a magnetic field for every atom, extraordinarily strong. Put all these magnetic fields together, if they're all aligned, well, that would be kind of disastrous. Okay. They don't align because of thermal excitation and stuff like that. That's coming out way too high. I'm not sure what's wrong with my thinking or something is. Um, what I want to get to is the idea first of a current loop. And within a magnet, or within any material, you've got these current loops. Every atom gives you a current loop, but they're typically arranged in random directions. They don't reinforce, they don't all align in the same direction. That's because of thermal energy, the 3/2 kT thing, average kinetic energy per particle. Okay. And that's giggles them around where they can't all point in the same direction. It would be a disaster if they could. They have extremely strong magnetic fields. Okay. Don't want to say too much more about that. We work through all this in the transition problem. Okay. If you have a current loop, we're getting current of say 1 amp through a loop diameter of radius 10 centimeters, let's say. You can work out that. So let's just look at what that would be. That's a pretty big loop. Up here, at delta L, you got the center. There's your orbit. Does that make sense? Okay. Now, I've mentioned this before, but let's just look at it again. You do your I delta L cross R. Multiplied by I delta L, it'll be like 1 amp delta L. And this R that we're crossing with is a unit vector. Okay. There's the magnitude. And by the right-hand rule, the field at the center is out this way. So root. total field, you'd add all these up. Well, the 1 amp and the 0.1 meter squared is the same for every delta L. So you just factor that out and just add up your delta L. I should write it bigger. Let's move over here. I'll just use symbols. Oh, of this, which is the magnitude of the field you get at the center due to this delta L length increment. K prime I and R are all the same for any length increment we want to use around the whole circuit. Okay. So when you add these up for all the increments around the circle, you could factor out the K prime I over R squared from the sum and just add up your delta L. But all your delta L's just add up to the circumference in the circle, which is 2 pi R. Now, if I is 1 amp and R is 1/10 of a meter, /60 times K prime, just put in the numbers with the units and you work out the units. K prime is 10 to the -7th. And you get something like 6 times 10 to the -6th decimal. You can verify that calculation. But if I is 1 amp and R is 1/10 of a meter, I is about 6. Comes out like that. The okay, when we wrapped this 1.5-inch pipe with a bunch of wire, we got, oh, I'd say 10, got something on the order, not quite 100 loops of wire around it. Okay. Each of those loops will contribute at its center okay. It's going to be a little bigger than this if we run an amp through there. And just, consider what happens if we run 1 amp through here. We don't want to run too many amps, so we're probably going to run anything from a fraction of an amp to a few amps. We don't want to melt the wire. Wire will handle a lot of amps. Okay. How does this compare with this? Let's say we're running an amp. We can just safely run an amp through here. Okay. We're running an amp through here. Loop radius isn't 10 centimeters. 10 centimeters is about like that. That would be a radius about like this. It'd be a circle about this big around. Okay. What's the radius here? Well, if this is 1.5 inches, the radius is going to be 3/4 of an inch. Outer diameter might be closer to 2 centimeters. Outer radius, outer diameter might be closer to 4 centimeters. The radius of these loops is on the order of 2 centimeters. So how would that change this result? Instead, we just still got 1 amp. We've only got 2 centimeters instead of 10. What's that going to do? To your result, it's going to increase it by what factor? 2 centimeters versus 10 centimeters, that's 1/5, right? So your R would be 1/5 as great. So this would be 5 times as great. This gets you up to 3 times 10 to the negative fifth Tesla. That's what you should do. Let's we talk for a minute. Okay, well, what you said is anticipating what I'm going to say next. If all these loops were in the same plane, then they'd all have the same center. But the centers of these loops, they'll go from, in here all the way out. The centers for the loops are spread out. And we looked at the situation previously where you've got a loop and you've got, let's say, a z-axis here, then you want the current at a point along the z-axis, right? Well, in this case, your I delta L or your QV, whichever you want to do, they'll still be perpendicular, but R is going to be a lot bigger up here than it is down here, okay? So this R might be 2 or 3 times as great as this R, so you get much less effect. And also, the magnetic field is at an angle. Now, we did that with the right-hand rule, and you see that the magnetic fields at this point, if you look at this thing just from within the plane of the loop, you're going to have magnetic fields that go like this. And the horizontal components of the fields from opposite sides of this thing, okay, will cancel each other. You only get the vertical component. So for a lot of reasons, the magnetic field you get here is a lot weaker than the magnetic field you get at the center of the loop. So if you want to look at the magnetic field here, let's just say at this point, just inside the surface, okay, you've got a bunch of loops here, 5 or 6 loops. It probably give you about this 3 times 10 to the negative fifth Tesla field, okay? But then they start falling off. By the time you get out here, you're probably down to just about a 10 to the negative 6 Tesla field, a much smaller field contribution up here, okay? And that's a little bit complicated to model, especially since these things are quite uniformly distributed, but we can tape it down and make them relatively uniform. Okay. But you could analyze it based on this fairly simple model that you will see before we get deeply into this stuff. Okay. Now, your 3 times 10 to the negative fifth Tesla field that we get from one of those loops with an amp is on the same order as the magnetic field of the Earth. So what do we see when we put the compass there? Okay. Well, what we see, if we just have a single loop, we'll see the compass needle deflect a little bit, assuming that the loop is oriented so that its magnetic field is perpendicular to the magnetic field of the Earth, right? Then we'll see some deflection. If the field deflects the needle of the compass by 45 degrees, that means this field should be about equal to this field, right? Okay, just, think of the vectors. 2 equal vectors perpendicular to one another are going to give you a vector that's at 45 degrees to both of them, right? And draw a picture of 2 equal vectors perpendicular to one another. What's the result? Right there's the result. These things are equal. You got an isosceles triangle. Okay. Where these 2 angles here are 45 degrees. If the Earth's magnetic field is here and the magnetic field of the coil is stronger, it's going to deflect more. All right, so what's going to happen if we have a compass with 1 amp running through all that stuff? You probably have on the order of more than 10 to the negative fourth Tesla, you probably have 10 to 20 times field of the Earth's magnetic field. So the compass is just going to go almost dead straight in the direction of the field you get there. Okay. I'm just doing some overview ideas that you kind of want to think about as you're working through these transition problems. We'll work out the detailed mathematics when we come to it. If you've got a current looking end on, so this is like you're looking at a current carrier, okay? And you're looking just at it from the end. So all you see is the end of the thing. And if the current is out of the board, then the magnetic field is going to be in this direction. It points, well, okay. Magnetic field is going to surround this thing. So that makes sense. Now, if this is a current carrier and you put a compass on top of it, well, magnetic field is going to deflect the compass needle. Okay. At the very top, the thing is horizontal, the compass needle will deflect accordingly. If you put the wire over the top, the compass needle will deflect in the opposite direction. Okay. Now you've seen that. So that's something you should understand pretty well. If you have a bigger circle out here, magnetic field still surrounds it, but it's going to be a smaller magnetic field. It's not hard to see that the magnitude of the magnetic field. They'll just indicate with B, no arrow over it, so we're just talking about magnitude. Okay. Is proportional, inversely proportional to the distance. So the integral of the magnetic field blue is the same over loop. Now we can work out the details of that. But this is your first look at what we call Ampere's law. It's much like Gauss's law. Now you have seen and should be pretty familiar with, because we talked about it in class, as well as you've been responsible for it for a little while, and set two of the transition problems. How you do Gauss's law for a straight charged wire with cylindrical Gaussian surface, and you find that the field falls off proportional to, inversely proportional to distance. It's not a reciprocal square, just a reciprocal relationship. This is very much analogous to it. Okay. And we'll derive it, but not really, because it really requires a little calculus that we can assume in this course. Okay. Now this integral of B dot dr, this just means we add up the magnetic field times delta L for every delta L around the loop. Okay. And here we add up the magnetic field times delta L all the way around the loop, like we did with the current loop. Okay. And what you get is, since the magnetic field is the same at a given distance, we assume these are circles concentric with the current. If you double R, you get half the magnetic field, but you get twice the circumference, right? So in this case, this integral just comes down to the magnetic field times circumference. And if magnetic field is inversely proportional to the radius, the circumference is directly proportional to the radius, so that the magnetic field, when you add up magnetic field times your length increment, it comes out the same. Okay. Now, it's still true if you do some irregular surface around this, or some irregular loop around here, some irregular path, some ellipse or whatever, but you don't have a uniform magnetic field on that ellipse. So it becomes fairly challenging to do that integral. And that's not really totally important. Just like with Gauss's law, we want to apply this to simple situations. We apply Gauss's law to spherically symmetric charge distributions, and we get an inverse square type of law. Okay. We apply it to line charges, and we get just an inverse proportionality, not an inverse square. We apply it to surfaces. Remember what we did with the photometer and the screen. Okay. And we see that the field is pretty constant as long as we don't get too far from the screen. Okay. And we talked about it with the capacitor. Symmetries of why the magnet or the electric field is perpendicular to capacitors at points that aren't too close to the edge. Okay. So just invoking those ideas and put those together rigorously. Well, we can apply this to this just depicts this thing, right? Bunch of loops spread out. This is what's called a solenoid. If all the loops are in the same plane, then it's a coil. Okay. Now that terminology is very. If those loops are all in the same plane, then the situation is just like this. It's just that you got a bunch of loops that more or less coincide. Okay, they can't really coincide because the loop can't, the wire, one wire can't be inside the other. But let's say we've got these wires wrapped around here, but very close to the same plane. Okay, and not too much thickness here. Okay, so they're pretty much modeled as, let's say, 100 loops at some average distance from the center. They're not spread out like this. Okay, these are the loops that we see. They're a bunch of loops. Okay. We want to calculate the magnetic field inside. And we do that by using a path that looks like this. Now this path goes to the inside of the cylinder. And that path is cut by the way I've drawn it here. Whatever the current in this wire is, it cuts this path 1, 2, 3, 4, 5, 6 times the way I've drawn it. Okay. I don't want to state the whole law right now. It requires just a little more than I want to lay on you, but if you cut the path one time, it would be analogous to this. Okay. It cuts 6 times over a certain distance here. You have a magnetic field inside here. Let's say in this direction. Okay. That would correspond to coming around the loop this way. The integral of your BDR across this distance is determined by how many times this current cuts this big path here. Magnetic field on this path, if we think of a path around this loop like so, magnetic field as we go from here to here is pretty much equal to the magnetic field we'd have if we went from here to here. So if we go this way on this path, come this way on this path, if we multiply the magnetic field times our distance here and here, it's in opposite directions, so it cancels out. And then we can make this path go as far as we want, so that the magnetic field across this part is essentially zero. So the only place the magnetic field has any contribution on this loop is the part that's inside the solid. Does that make sense? I'm kind of waving my hand over that. It's worth doing rigorously, but I want you to get the idea in your head. This is called Ampere's law. And this is how you figure out the field through the solid world. Okay? Or the field inside a solid. And you're talking again about essentially breaking this path here up into little segments. Each segment on this side is traveled in the direction opposite to the corresponding segment on this side. So magnetic fields are pretty much the same here as they are here. The magnetic field here is pretty much the same as it is here, but since you're traveling in opposite direction, the two contributions to the total magnetic field around the loop, total magnetic field times your length increments. Contribution here equal and opposite contribution here, contribution out here negligible, because this can be as far away as you want it to be. And then all you've got is here. So that if this distance is L, we're called, I'm talking about the blue loop, not the loops of wire around the loops of wire cut the blue loop 6 times according to this picture. And then we got a definite expression for what this would be, which we can easily derive. You're going to see it in the transition problems, which is why I'm talking about them. See how some are related to. So we'll flesh out this idea, but we'll take plenty of time to do it. Once you're familiar with the little blocks that you get in the transition problems, we put them together into bigger blocks, and we can do some pretty neat stuff. And Ampere's law is pretty neat. This is basically one of Maxwell's equations in form. Now they're originally 10, they got consolidated and so forth, but it comes down to 4 equations. Okay, govern electricity and magnetism, everything. I'm not going to tell you what those equations are. Already seen in tangible form what they mean. Okay, like we know there's a field inside this solid. We've seen that. This is how you analyze that field. We know there's a field at the center of the loop. We've seen that. It's by selecting a magnet, maybe cranking the generator so we can actually feel what's going on. And the last thing mentioned is you got a charge Q moving at velocity v inside a magnetic field. And the force on the charge, the force V is just V cross V. And in the case of a current carrier, IL cross V. A QV is equivalent to an IL. It has the same units, has the same meaning, and it's a little bit tricky to understand exactly why a QV and an IL come down to the same thing, but we'll work that out. And again, I think you will encounter it in the transition. Okay. So what that means, let's say I've got a current in this wire. We've got the magnetic field of the Earth. It's in about this direction, not quite perpendicular to this. It's in a direction like this. Okay. We got a current in this direction, and we got the length of this thing, about a meter. Okay. Let's say we got 100 amp current running through this thing. It's a meter, so that's 100 amp meters, right? That's your IL. It's got a direction. Okay. Say direction of the J vector. Let's say that the Earth's magnetic field is 3 times 10 to the negative 5th Tesla in the direction of negative I vector plus 0.3 times the J vector. Okay. Well, you can express that as a vector and you can do cross product, IL cross B. IL cross B gives us a force in this direction. Okay. If I've got 2 parallel wires, I don't have 2 things to use for wires. I've got 2 parallel wires. Each wire produces a magnetic field. And on picture, magnetic field surrounding the wire, right? If the current in this wire is in the same direction as the current in this wire, then the current in this wire responds to the magnetic field from this wire. That magnetic field would be in this direction. If the current's in this direction, your IL cross B is like this, and you have a force here that pushes the wires apart. If the current's in opposite directions, opposite pull together. I think I've got that right. My gestures tend to indicate that. Work out the right hand rule, because right now you've got everything you need. However, you haven't thought through the problems, and that's what's going to be necessary to get a firm foundation so we can really understand these things. Right now, you've got about that much understanding if you understand just in general what I've been talking about. Build those blocks and that'll grow. And then we start putting those blocks together into bigger things, and you'll have a really good foundation for this stuff. I do. And y'all are smart, you're working. So I think it's going to happen. Last thing we want to maybe think about is wanted to mention this. If you've got a circuit, you've got some kind of a power source. And you got some kind of a resistance here. You got a capacitor here. Well, let's say this source could be an alternating source, like AC circuit. It could be something else. This is your symbol for like a battery. And this is a symbol for a switch. You've got a battery, switch, some kind of resistance, and a capacitor. You throw the switch. The capacitor initially doesn't have any charge on it. As soon as you throw that switch, you get a current. The current pulls negative charge off of one plate of the capacitor, puts it on the other. So the capacitor starts charging, which means the capacitor develops a voltage in the direction opposite to whatever current is, whatever the voltage of the source is. Okay? So the longer this runs, the more current you have, the more charge you have in the capacitor, the more voltage you have opposing the voltage of the source. So the current tends to do this. It exponentially approaches zero. Okay? There's your current. Here's time. Now, if you suddenly, let's say this is one of your generators, so you can suddenly reverse it. Well, you've experienced that. What happens when you reverse it? It's hard to crank. Okay? Because that's V low and V high. Let's say you start off with no voltage under capacitor. The voltage is going to exponentially approach this high voltage. Okay? Voltage of the capacitor will become equal and opposite to the voltage of your source or in the limit. Then you switch the voltage of your source down here, and the capacitor is going to exponentially approach this voltage. Okay? Then you switch again, it's going to exponentially approach this one. Switch again, it's going to exponentially approach this one. That may have to make sense. Okay. So this leads us to the whole idea of an alternating current. What if instead of switching suddenly from high to low or low to high, the current is now following a sine wave? Smooth current. Well, you know the differential equations, you can solve the differential equation. Okay. You're getting an intuitive idea of how all that works. And also, you know, what happens to the differential, what happens if you got some kind of complicated voltage, where it's hard to solve a differential equation. How are you going to conceptualize what's going on? Right now, I just want you to understand capacitor, the voltage on the capacitor will, because of the way the current increases and so forth, voltage of the capacitor will exponentially approach whatever voltage is produced by the source from whatever the voltage capacitor has to be at that time, but we'll deal with that. And we're a couple minutes over time, so we'll quit. So have a good break.